Hello all, this is Mr. G, and in this video we're doing Chapter 4, Section 1, and after today we should be able to graph quadratic functions by using vertex form. Graph quadratic functions by using vertex form. Now before we jump into our definitions and our examples, I want to make sure we remember what a quadratic function is. A quadratic function is very different from a linear function in that it's y equals x squared. The power of 2 is what makes it a quadratic function. So as soon as you see a power of 2, as long as that's the highest power, you should think, oh, this is going to be a quadratic function. That's a skill you really want to get better at as you grow in your mathematical careers. Looking at an equation and saying, oh, that's what this type of function is, and then knowing what type of graph it's going to make. But we'll get there. We'll get there. At this point, all you need to know is anytime you see a power of 2, as long as that's the biggest power, then it's a quadratic function. And we can use what's called vertex form to graph things a little bit more easily than it's in other forms. So vertex form is sort of like slope-intercept form. Like if we have y equals mx plus b, which we know is slope-intercept form, we know it's going to be a line, we know m is the slope, we know b is the y-intercept, but that's not the only form for a linear function. We also have point slope, y minus y1 equals m times x minus x1. And that's a different way for us to get information. We know that m is the slope and x1 and y1 are any coordinate, not just the slope-intercept of that graph. So the reason I'm sort of reminding you of all those things is I want you to keep those skills in mind as we attack and approach this vertex form. It's like, okay, so this vertex form, which is right here, is just a way for us to graph these functions. So let's take a look. Quadratic functions, one thing you need to know, they make a parabola, they make a U. Could be a right side up U or an upside down U, depending on the function we're given. And vertex form is f of x equals a times x minus h squared plus k. Now, based on previous videos, a lot of this should be familiar. Hopefully, you're looking at this negative h thinking, oh yeah, that's a horizontal translation. Looking at the k thinking, oh, that's a vertical translation. Remember those translation rules apply to all functions, so obviously it has to apply here. Now, I don't want to say this, the way the translation rules end up helping us graph is they give us the vertex. Because the vertex of the parent function starts at the origin. So if we have a coordinate plane here, the vertex always starts right there of our parabola. And then, that's kind of ugly. That's a little bit better, but whatever. And then, the h moves it left and right, the k moves it up and down. So h and k, whatever they are, end up giving us the vertex, the most important point of our graph. We'll see exactly how that works in an example in a second, but for now, just know hk gives us the vertex. We still haven't talked about a though, and a deserves a little bit more attention. So we got a whole slide just dedicated to a in vertex form. So a is the vertical stretch or the vertical compression. So it's almost like we're holding a rubber band or like an exercise band or something, and we stretch it vertically or we compress it vertically. Those are our two options. Now we get a vertical stretch whenever a is bigger than 1. So if a is like 2, 3, 4, 5, or even if it's like 1.5, any a value that's bigger than 1 will give us a vertical stretch. The way we get a vertical compression is if a is less than 1, but bigger than 0. So if we have something like 1/3 or 0.75 or 0.9, as long as it's between 0 and 1, we get a vertical compression. Now, one thing that's very important to know is that A tells us how to get to 1 point and only 1 point. That's so important, I'm going to repeat myself. A gets us to 1 point and only 1 point. It's not like slope in a linear function where we can do it over and over and over again. It gets us to only 1 point. And then when we get to that point, is if we go right 1, we always go right 1. I don't care what the a value is. We start from the vertex and go right 1, and then we either go up or down, depending on whether it's positive or negative, whatever a is. So if a is positive 3, after we go right 1, we go up 3. If a is negative 5, after we go right 1, we go down 5. But no matter what a is, we always go right 1. Now let's see how that looks with some brief examples here. Let me scroll down a little bit more. So here's what a vertical stretch would look like. If a equals 1, then, okay, from our vertex, we go right 1, because we always go right 1, and then we go up 1. That is the parent function of a quadratic. But if we stretch it vertically by 2, well, I didn't want to erase all of that. We'll just leave those arrows there, I guess. If we stretch it with an a value of 2, we still go right 1, but now we go up 2 to get to our next point, which gives us a skinnier looking parabola. Because think about it, if you had like a rubber band or something and you stretched it, it would, get skinnier as it's being stretched. A vertical compression, on the other hand, remember, that's if a is between 0 and 1. So if we had a equals 1/2, we would still go right 1, but now we would go up 1/2, giving us a compressed parabola, which ends up looking like a wider U. Because again, if we had a rubber band or something and we did this with it, it would like sort of stretch out and get a little bit more relaxed, as opposed to if it was stretched out vertically. All right, now let's jump into some examples. Oh, no, more vocab to go over. I forgot. There's still some vocab to talk about. So here we have two examples. My face is sort of in the way, so let's show the examples first, then we'll drag in the terms where they go. So we have, in the first one, we have a right side up view, and then we have an upside down view, which both of these are parabolas, both of these are allowed. Now, the axis of symmetry in both of these cases is the dotted line. So there's one axis of symmetry, there's the other axis of symmetry. Now, the axis of symmetry is really important because the axis of symmetry is obviously a line of symmetry. So that means any points we get on this side of our parabola, we can fold over and automatically double our answers. So the axis of symmetry is really powerful that way because it instantly doubles all of our answers. Next, let's talk about the vertex. So the vertex, hopefully, is that point right there or right there in the two situations. So the vertex is always either the top point or the low point of our parabola, which leads us right into talking about maximum or minimum. In the case on the left, the vertex is a minimum because it's the lowest point of the quadratic. In the case on the right, the vertex is a maximum because it's the highest point of that quadratic. Now, a parabola either has a maximum or a minimum. It will never have both. A quadratic, a parabola, will never have both a maximum or a minimum. It only has one, depending on whether the vertex is the low point or the high point. So keep that in mind. The last thing to talk about is what we call concavity, concave up or concave down. Now, you may not have heard this before, but even if you haven't, it's pretty much just what it sounds like. Concave up is this one, if it's open up, and concave down is the other one. I'll move my face in a second, where it's concave down. So essentially, if the parabola is opening up, it's concave up. If the parabola is opening down, it's concave down. Let's move that so it's a little easier to see. Right. Now we're going to take this vocab, a lot of vocab I know, and we're going to apply it to some problems. So we're going to do 3 examples in this video, and we're going to graph these parabolas and then identify all of the important parts, all of the important information. So it says graph the function and find the following information. So we got f of x equals x plus 4 squared minus 3. All right, now you don't have to write this down every time, but I like to at least think, okay, we're in vertex form. So it's a times x minus h squared plus k. That's going to help us find our information. That's sort of like our slope-intercept form. But obviously, it's vertex form this time because it's not a linear function, it's a quadratic function. First thing we always want to find is the vertex because that's the most important point. The vertex is always hk, remember. So let me see. In this case, h looks like it's a positive 4, but remember, we talked about this in a previous video. We always have to change the sign of h. So h is actually a negative 4, or I said that incorrectly. We have to change the sign of what it looks like h is. It looks like h is positive, but it actually comes out as a negative. With k, we don't need to do that. K stays negative. So it's negative 4, negative 3 is our vertex. Let me erase hk just so we have a little bit more space to show our work. Slide this over. So there's our vertex. Let's graph it. So I'm going to go to negative 4, negative 3. There's the vertex. Now, before we do anything else, I want to say, okay, let's remind ourselves. What always goes through the vertex is the axis of symmetry. You don't have to draw that in every time, but I like to at least imagine it there because that's going to give us a line to fold over to sort of double our answers from now on. So the vertex is the only point of the problem that's touching the axis of symmetry. And to name the axis of symmetry, it's just not negative 4, it's x equals negative 4. The axis of symmetry is x equals negative 4. If we just say negative 4, we're just talking about a number. But x equals negative 4 is the vertical line that we have there for the axis of symmetry. Another easy way to get it, it's always the x-coordinate of our vertex. Okay, what's next? Now we're talking about maximum, minimum, concavity, and domain and range. Let's finish graphing it first. Let's graph it from here. So let's see. We haven't used our a value yet. We used h, we used k. Now let's use our a value. And the a value might be kind of tough to see there because it looks like there's no number here, but there actually is an invisible 1 in front of the parentheses, so our a value is 1. But no matter what the a value is, we always go right 1, and then we go up or down whatever a is. A is a positive 1, so we go up 1, and that leads us right there to that point. So that's what 1 point A can get us to. We cannot repeat this. All right? And we'll talk more about why we can't repeat this at the end of this example, once we have it all graphed. Now that we have that point, we can fold it over, and we've doubled our answer. So I guess technically A gets us to 2 points once we have the axis of symmetry. All right, now we're all out of tricks, and I want to find one more point here to make sure our parabola is at least sort of accurately drawn. I mean, because if we just sort of try and draw a U from here, like I don't know if it's supposed to be like that, I don't know if it's supposed to be skinnier. I'd like to get at least one more point here to make this a little bit more accurate. And the only way to get one more point is to plug in an x value. That's what we're going to do here. We're going to plug in an x value. Now, we can plug in any x value, but to make this easy to graph, let's think about this. We had the vertex at x equals -4. Then our a value brought us to x equals -3. Let's plug in x equals -2 and see where we end up. Let's give a domain value of -2. You don't have to do that, but that's going to make our lives a lot easier. So that becomes -2 plus 4 squared minus 3. Just plugging it directly into our f of x function. And let's see, what does that give us? That's -2 plus 4, that's 2 squared, minus 3, that's 4 minus 3, we just get 1. Hopefully we can handle doing that in our head or in a calculator, it doesn't matter. So that means the coordinates are, what was the x value we plugged in? -2, and the y value we got was 1. We entered the domain of -2, got out a range of 1. So I go to -2, 1, and then we use our axis of symmetry. It's 2 steps away, so 2 steps away on the other side gives us -6, 2. And this is our parabola. Again, it's not going to be perfect, but something like that. And there we go. Now let's go back to what I said before about how A only gives us 1 point, at least on one side of the parabola. The reason we cannot keep going is because if we keep going, we're not going to get a parabola. Like if I went right 1, up 1, right 1, up 1, right 1, up 1, we end up with a V. And that would be an absolute value function. So that's what makes, I don't want to say this. In a linear function, the fact that we can do the slope over and over and over again and it still works as a function is actually really special. That only works for a linear function. It sort of works that way with an absolute value as well. But any other function, like a quadratic, a cubic, certainly any trig functions, you're only going to be able to do things like our a value one time. Okay, now we've got to find our maximum or minimum. We see the vertex right here is a minimum. It's a low point. So the minimum value, that's going to be, let's think about it. Maximum or minimum, we're talking about height, so that's high or low. So that's only the y value. So the minimum value here would be a -3. -3. And again, you can just look at the vertex. It's the y value of the vertex. That can make things a little bit easier. Now, some students get confused and they think, well, wait a minute, this -4 is a part of that minimum as well. That's a part of the vertex. But -4 is not the minimum x values. You know, -5, -6, -7, those all still work. So there is no minimum for the x, only for the y. Now concavity, it's concave up. And now it's time for our domain and range. The domain is nice and easy for a quadratic. It's always all reals. All reals. If you want to put that in set notation, that would be from -infinity to +infinity, if you want to write it that way. The range value, let's see. The minimum value was the range, the y of -3. So the range is all reals where y, running out of space, all reals where y is greater than or equal to -3. So our minimum is -3, and the range values above that all work. And if you wanted to do this with set notation, let's scroll down a little bit. So let me see, that would be starting at -3 and going to +infinity for our range values. So that's example 1. A lot of information just in this one example. Let's do 2 more. So here's example 2. We got to graph the function and find the following information. Same directions as last time. We're going to run through this hopefully a little quickly. So let's see. The vertex h and k. The h value is -5. There's no k value, which throws some students off sometimes, but that just means the k is 0. There's a k value of 0. So -5, 0 is going to be right there. All right. Now the axis of symmetry, we know that goes right through our vertex. So the axis of symmetry will be x equals -5. Remember, it's always the x coordinate of the vertex, the axis of symmetry. Let's finish graphing before we do the max min or concavity or any of that stuff. So we use our a value, which here is a negative 1/2. So we go right 1 from the vertex, because we always go right 1 from the vertex. And now it's a negative 1/2, so we're going to go down 1/2. So we're sort of in the middle. I know my point's not perfect there, but we're just going to do the best we can. Now we fold it over, and there we go. Remember, even though a is a fraction, we always go right 1. Now, to find a third point, we just plug in an x value. So we just did x equals -5, x equals -4. Now we need x equals -3. So I'm going to plug that in and find a coordinate. It's going to be -3 something. So I plug this in, it becomes -1/2 times -3 plus 5 squared. Let's see what we get. -1/2. Let's do some of this in our head. So -3 plus 5 is 2. 2 squared is 4. So that's going to be -2. -3, -2. So -3, -2. And fold it over. 1, 2, 1, 2. There we go. And that gives us a little bit of a wider parabola. I know the drawing's never going to be perfect, but just as long as we're relatively close. Actually, that second half looks kind of hideous. Let me try that part again. I think I can do better. There's one, and there's the other. I know it's still ugly, but at least we have 1, 2, 3, 4, 5 important points that are graphed there. All right, now maximum or minimum. We can see that the vertex right here is a maximum. It's the highest point. And the maximum value, the highest y value gets to is actually just 0. It's all in the negatives. Concavity, we see it's open down, so we say it's concave down, concave down. Now for domain and range. Domain is easy for a quadratic. It's always all real numbers, which I just say all reals for short. And the range, let's see. The highest it gets to for the y values is 0. So that means it will be all reals where y, let me just write it here, y is less than or equal to 0. So basically, the highest we get to is 0. So our range values will always be less than or equal to 0. If you wanted to do this in set notation, that would be from -infinity to 0 inclusive on the 0 side. So that's another way to write it. It's the same exact thing. All right. 2 down, 1 more to go. Pause the video right here. Give this problem a shot. Come back when you think you have an answer. 3, 2, 1. Let's go. All right, we know what the directions are. Let's just jump right in. Let's find our vertex, which is h and k. There actually is no h value here because there's nothing like being added or subtracted with x, like in parentheses, with before it's squared. So the h value is 0, and the k value is -6. So don't get thrown off if h or k are missing. That just means it's a 0. So I go to 0, -6 for the vertex. Now the axis of symmetry is going right through that. So that would be the line x equals 0. And let's finish graphing this before we get the rest of it. So our a value is 2. That means from our vertex, we go right 1 and up 2. Since our a value is a positive 2, so that puts us right there. Use our axis of symmetry to fold over. And there we go. Now to find our last two set of points, we need to plug in a number. Let's see. The vertex was at x equals 0, then x equals 1 for our a value, and then let's plug in x equals 2. Or our a value gave us an x value of 1. Whatever. So we're plugging in 2. That's the long and short. It's going to be 2 something. So it's 2 times 2 squared minus 6. It's supposed to be a 6. Let's see. 2 squared is 4 times 2 is 8. So it's just 8 minus 6. That's 2. So 2 and 2. That's nice and convenient. So we go to 2, 2. Fold it over. 1, 2, 1, 2. And there we go. We get a very skinny parabola there. My drawing's never perfect. That's why we have the important points there. Okay, now it's time to fill in our information. So we see a minimum value. So it's a minimum because the vertex there is the low point. And it's a minimum value, a y value of -6. That's as low as it goes. And the concavity, it's concave up. Concave up. The domain, we know that for a quadratic, it's all real numbers, all reals for short. And the range value, let's see, there's a minimum, so it's going to be all reals where y is greater than or equal to -6. And if you want to write that in set notation, that would just be from -6 to positive infinity for the range values. And we are finished. Hopefully this made sense. If you have any questions, let me know. Enjoy the rest of your day.